difficulty as opportunity. This is true in these days. We're faced with realities around COVID, but it has also been true throughout history. Today's lesson is going to talk about a direct application of LeChatelier's principle with equilibrium chemistry. I'm going to include with it a story, without any judgment, for you to view on your own. Back before the development of the Haber process, people had problems producing ammonia. Ammonia is really useful for a fertilizer to help plants grow. Many people around here use ammonia. We produce ammonia at the Coke plant just down the road from our high school. But Haber, during the war, developed a process that made the production of ammonia more effective. He didn't produce it for fertilizer. During the war, the Allies had claimed ownership of the saltpeter piles in Chile, where we got most of our nitrate sources, and a lot of munitions and bombs require large amounts of nitrate. The Germans weren't able to get it, so they had to find a way to produce their own. In France, Haber developed a process to do this. You have this equation in your notes, and this is the Haber process for the production of ammonia. Now, when we go to produce ammonia, we take gaseous nitrogen, of which the air is 78% nitrogen, so there's lots of it available. And we react it on a 1:3 ratio with hydrogen. The most effective source of hydrogen gas is actually from a reaction where hot steaming water under very high pressure is reacted with methane gas, and that actually strips the hydrogen off the methane gas. Now, when we take the nitrogen and the hydrogen and react them together, we can make ammonia, and it's an exothermic reaction that also produces heat. So here's the problem with this reaction. The KEQ for this reaction is much, much less than 1. This reaction strongly favors the reactants, so much so that when equilibrium sets up, we have lots and lots of reactants and almost no products, which makes it kind of a crappy reaction in terms of industry. You mix all these reactants together, and as soon as they're made, they immediately decompose back into the reactants. And so, using LeChatelier's principle, we can actually encourage this reaction to proceed to the right and form more ammonia. There are 3 things that we can stress the system with: pressure, concentration, and temperature. Now remember, our desired effect is to force this reaction to shift to the right. We want more ammonia gas. So what should we do with the pressure? Should we increase it or decrease it? In order to decide that, we need to look at how many moles of gas there are. On the reactant side, we have 1 plus 3, we have 4 moles of gas. When they react to the product side, we have 2 moles of gas. Moving in the forward direction would have the effect of reducing the amount of moles of gas and therefore reducing pressure. If that's what we want to happen, then what we need to do is increase the pressure. Because if we increase the pressure, the system will want to decrease the pressure and therefore will shift to the products, the side with less moles of gas, and that will have the effect of decreasing the pressure. We know when we shift to the right, that means that we'll be producing more ammonia. And so anytime we do this reaction, it has to be done under high pressure in order to get a large supply of ammonia. Okay, well, what can we do in terms of concentration? Again, remember, our desired effect is to have a shift to the right. Now, there's 2 things we can talk about in terms of concentration. We can talk about the reactants or the products. If we increase the concentration of my nitrogen and my hydrogen, then the system will want to decrease them. And it decreases them by following the forward reaction, because in the forward reaction, the nitrogen and the hydrogen get used up to form ammonia. So we can see that increasing the concentration of nitrogen and hydrogen will then shift again to the right, make more ammonia, take that excess nitrogen and hydrogen away. We can also affect the concentration of the ammonia itself on the product side. Again, if what we are wanting is to have my reaction shift towards ammonia, then what we want to do is decrease the concentration of ammonia. Simply running water down the inside of the tank will cause the ammonia to dissolve into the water. It's highly soluble in water, and remove it from the equation. If we remove ammonia as it's produced, then the system will try to replace that ammonia by making more of it. Again, it causes the reaction to shift to the right. We have one more thing that we can affect, and that's temperature. But this one is a little tricky. When you first look at the equation, we can see that heat is being listed as a product. And so if I want to get this reaction to move towards the product side, towards heat, what I would initially think that I'd want to do would be to cool it off. A cool temperature would actually cause the reaction to want to heat back up and move towards the word heat. But this is kind of a double-edged sword, because if we take a look at a reaction diagram for the production of ammonia, my nitrogen and my hydrogen have a given amount of energy, and I can see that my ammonia will be somewhat less than that because heat is being released. The problem is the activation energy for this reaction is very high. If I cool this reaction down too much, my nitrogen and my hydrogen will not have enough energy in order to reach the activated complex, and no reaction will occur. So the problem is that we need to keep the temperature cool enough to favor the forward reaction, but hot enough to make that reaction occur at all. The way we do that is by lowering the activation energy. What can we do to create a lower energy pathway so that we don't have to get the reaction chamber as hot? The answer is to add a catalyst. And effective catalysts are valuable industry secrets because a good catalyst allows us, with a minimum amount of energy, to have a forward reaction that still favors the production of ammonia. Now, in this screen, we see the application of LeChatelier's principle to get the desired result we want and have the production of ammonia favored in a reaction that doesn't naturally occur on its own. But I also told you it was a story. Remember, Haber didn't do this reaction for the good of mankind. He did it to make ammonia as a starting point for nitrates and fertilizers for the war effort. There's more to the story than that. Another one of the equilibrium reactions that he created with all of his war efforts was the formation of mustard gas. In July of 1917, a yellowish, kind of a shimmery cloud that was floating around the soldiers caused a horrible reaction in their skin because it's a skin-dissolved gas that made really bad blisters and sores. People started coughing up blood, and it was very, very deadly. The gas was named mustard gas because of the mustardy type smell based on the sulfur in it that was formed. So we have this man who has created two sort of weapons that could be used for warfare. But the deal is that the Haber process after the war became so valuable with regard to the industrial production of ammonia-based fertilizer, and it made a huge role in avoiding worldwide famine, and now is responsible for feeding over a third of the world's population. It won him a Nobel Prize in chemistry. So this discovery that he made, while could be used for evil, has also saved hundreds of thousands of lives. Now, that's great for his Haber process, but what about his mustard gas? Because the story continues. You see, at the end of World War I and decades later with World War II looming, researchers were worried that mustard gas was going to get used again, so they started trying to look for an antidote to it. And there was two doctors in the United States at Yale University. There's Louis Goodman and Alfred Gilman. And they were really looking at mustard gas. And they noticed something really interesting. They noticed that the records of soldiers who were affected by mustard gas had really low numbers of immune cells. The kind of cells that, if mutated, develop leukemias and lymphomas. And they thought that this was absolutely fascinating because what they discovered, if mustard gas could destroy normal white blood cells, it could probably also destroy cancerous ones. And mustard gas, also developed by Haber, became the catalyst for the discovery of what we now call chemotherapy, which has also saved millions of people, many of whom you know. I told you that I wouldn't leave you with any decision on the matter. It's up for history to decide whether these inventions were good or evil. They've been used for both, and probably would serve to make a great debate paper in an English classroom. But this is a chemistry classroom, and we're looking at equilibria.